Hi guys, welcome back to my channel. I hope you had a wonderful holiday break and a lovely new year. Today we're going to talk about the moon's surface and inner structure. So first we'll go through some vocab words that will come up in the video. Then we'll talk about the surface's elemental composition, a quick run through the giant impact formation theory, and the timeline of the geologic history. After that, we'll take a closer look at what makes up the lunar landscape, the lunar magma ocean and lunar rocks. We'll delve into the internal structure of our moon. Finally, we'll end off with a fun space meme. So this is the vocab that will be relevant in today's video. To start with our vocab, we have epoch. An epoch is defined as a period of time that is defined by evidence in rock layers. Breccia is the fragments of different rocks being melted together through meteorite impacts. Sedimentary rocks are formed through the deposition and solidification of sediment, especially sediment transported through water, ice, and wind. Igneous rocks are rocks formed through cooling and solidification of magma or lava. So let's start off by discussing the elemental composition of the lunar surface. Here I compiled a pie chart on Excel of the elements that are present. It is important to note that these are the individual elements and not the compounds that they make up. Oxygen is the most prevalent element, composing approximately 60% of the lunar surface. Silicon, aluminium, calcium, magnesium, iron, and titanium also make up a large part of the moon. We'll go into more detail later on in the video when we talk about the materials that make up the lunar highlands and lunar maria and how they differ. The most widely accepted formation theory as to how the moon was formed is the giant impact theory. This theory states that Theia, a Mars-sized Earth Trojan, crashed into the Earth, causing debris to fall around the Earth and start to orbit it. The debris ended up becoming the moon. If you'd like more information on lunar theories, a great video to watch is my previous video where we discuss the theories in more detail. I'll link it down below in the description. So now that we have the basics covered, let's talk about the moon's timeline of geological history. A vocab word that comes up in this section is epoch. As a reminder, an epoch is defined as a time period that is defined by evidence in rock layers. The lunar formation is categorized into 5 major time periods: the pre-Nectarian period, the Nectarian time period, the Imbrian period, the Eratosthenian period, and the Copernican period. The pre-Nectarian period represents the time from the formation of the moon's crust to the formation of the near side of the moon, which was the Nectaris impact. The Nectarian period represents the time from the formation of the Nectaris impact basin to the formation of the Imbrium impact basin. The Imbrian period is actually split up into 2 separate epochs, the early Imbrian epoch and the late Imbrian epoch. The early Imbrian epoch represents the time between the formation of the Imbrium impact basin and the formation of the Oriental impact basin. The late Imbrian period represents the time between the formation of the Oriental impact basin and when the craters with the size of DL, or the largest craters that we've seen on the moon, started to get obliterated by space weathering and erosion. The Eratosthenian period of time basically just represents the time that it took for the DL craters to completely get obliterated. And finally, the Copernican period is the period that we are in right now. Keep in mind that the Copernican period has no relation to the Copernicus crater. This is a timeline with the different time periods of time being put into a visual perspective. The pre-Nectarian period lasted approximately 613 million years. The Nectarian period lasted approximately 70 million years, early Imbrian approximately 50 million years, late Imbrian approximately 600 million years, Eratosthenian takes the cake in terms of time, lasting a full 2,100 million years, and finally the Copernican period, extending to present day, has lasted for 1,100 million years, with more years still being added as it is our current time period. Okay, I'm sure that was a lot of information being thrown at you, but I promise that this section will be lighter. Now, without further ado, let's get into the details that make up the lunar landscape we all know and love. First off, let's talk about two major landscape features, lunar maria and lunar highlands, also known as lunar terra. Lunar maria is the really dark stuff that astronomers mistook for seas, which incidentally is what it means. It's directly translated to the seas of the moon in Latin. To most people's disbelief, the maria only takes up approximately 17% of the lunar surface. This is because it is mainly found on the near side of the moon, which is the side that we always see. Now, something else you'll notice is that the moon is made of primarily igneous rocks, while the Earth is made out of sedimentary rocks. The lunar maria gets its dark color from dark basalt composed of iron, magnesium, and titanium. Basalts form from rapid cooling flowing lava. We can see other clues of lava activity such as rilles, domes, wrinkle ridges, and grabens. Rilles are long, narrow dips in the lunar surface that look like channels. They are thought to have been formed by lava channels. Domes are a type of shield volcano that are typically seen on the moon. Wrinkle ridges are low, curvy ridges that are a resultant of compressive tectonic forces. Grabens are also formed as a result of compressive tectonic forces. I'm going to discuss the moon's recent tectonic action and the resultant moonquakes in a future video, so stay tuned. Let's move on to the lunar highlands. Lunar highlands, also known as lunar terra, make up the other 83% of the lunar surface. The highlands have a lighter color and are made up of anorthosite. Now, something to note is that anorthosite is created from lava that cools more slowly than lava that forms basalts does. This implies that the lunar maria and the lunar highlands are created under differing conditions. I'll go into more detail later in this video. Breccias are fragments of different rocks melted together through the impact of meteors. The breccias are found in both lunar maria and lunar highlands, but they are much more common in the lunar highlands. Next, let's talk about impact craters. Craters are created when a solid object, such as an asteroid or meteor, hits the moon's surface with a high velocity. Craters can not only leave an impact on the surface, but can also create ejecta and ray systems. Generally, most craters are circular because the crater happens to be similar to an explosion, which are symmetric in shape. As time has passed, the size of craters has been shown to decrease. This is a phenomenon called the SFD, or size frequency distribution. As we discussed in the timeline of the moon's geological history, we know that all of the largest craters created in the moon's developing stages have been destroyed in the Eratosthenian period. Scientists have observed that younger, smaller craters are bowl shapes with sharp rims. On the other hand, larger, older craters have curved terraces on their inner walls. The oldest craters we can observe are impact basins, which sometimes have multiple circles of inner walls. Something interesting to note is that because of the materials under the moon's regolith, younger craters have a higher albedo, meaning that they are brighter and more visible. As time passes, space weathering decreases a crater's albedo. The older the crater is, the smaller the albedo is, which is why older craters are darker and less visible. Okay, on the previous slide I mentioned that regolith is important to the albedo of craters, but let's look closer at what it's actually made of. Regolith contains rocks, minerals from the original bedrock, and glassy particles that are created during impacts. The chemical composition of regolith is dependent on the location of the regolith. In the lunar highlands, the regolith is composed of aluminum and silica. In the lunar maria, the regolith is rich in iron and magnesium. The amount of regolith also depends on location, as the younger lunar maria only have approximately 2 meters of regolith, while the oldest lunar highlands have up to 20 meters of regolith. Lunar soil refers to regolith that is very fine, and lunar dust refers to regolith that is even finer than lunar soil. So something interesting that I came upon in researching for this video was that regolith could offer clues as to how the sun's activity has changed over time. Different elements the sun emits in the form of radiation and solar wind could, such as helium, neon, carbon, and nitrogen, could be absorbed by the regolith. Because of this, it is possible to take a closer look at how the sun's activity has changed over time. Let's move on to the underground of the moon. Similar to the lava tubes on Earth, lunar lava tubes are underground tubes that were formed by flowing lava. There have been several ideas to use these tubes as structures for future lunar bases, as they protect from aspects of the moon's harsh environment, such as meteorite impacts, solar radiation, and extreme temperature changes. These have been popular in both science and science fiction. Let's talk about the lunar magma ocean. The lunar magma ocean is based off of the giant impact theory. Reminder, the giant impact theory states that Theia crashed into Earth, causing debris from both objects to fling into orbit around the Earth, eventually forming the moon. Okay, according to this theory, the moon would have had to been very hot to successfully combine into one object. Well, a large portion of the moon was once melted, and it was known as the lunar magma ocean. Now, in this diagram, we can see that because of the existence of the completely molten magma, we can see that the elements of olivine and pyroxene would have sunken down to the bottom of the magma ocean, and feldspar would have risen to the top to become the anorthosite crust. Since we know the lunar highlands to have an anorthosite crust, which is high in the concentration of creep, we know that this is true. Okay, you might be asking, what is creep? Let me explain. Creep is a geochemical component. Creep is actually an acronym that is made up of 3 different parts, K, Re, and P. K stands for potassium, REE stands for rare earth elements, and P stands for phosphorus. Let's go a little more in depth and talk about lunar space rocks. Lunar rocks are made out of similar materials as on Earth. As we saw on the diagram in the previous slide, pyroxene and olivine are mainly seen in the moon's mantle, whereas plagioclase feldspar, also known as anorthosite, is seen mainly in the moon's crust on the lunar highlands. Brachias are mainly found in the lunar highlands, but they're also found in the lunar maria. Brachia has 3 subcategories based off of how it was created: fragmental, granulitic, and impact melt brachias. Ilmenite is common in mare basalts. Creep basalts are also found in the lunar maria. Auremalcolite is actually an element that we don't naturally have here on Earth. It was discovered by and named after the Apollo 11 astronauts. Armstrong, Aldrin, and Collins. Alright, let's wrap up today by talking about the internal structure of the moon. The moon's low bulk density suggests low metal abundance. The crust is estimated to be approximately 50 kilometers thick, plus minus 15 kilometers, because the far side, which has less lunar maria, is 15 kilometers thicker than the near side. The moon's magnetic field is obviously weaker than that on the Earth, only being approximately 1/6 of that of the Earth's. The lunar magnetic field also isn't a dipolar magnet field, meaning that it doesn't have two different poles on either end. In fact, the moon doesn't even have a global magnetic field. But some of the lunar rock samples that were brought by the Apollo astronauts do suggest that in the early Hadean eon, when the moon was being formed, the moon's magnetic field was very strong, ranging from 20 to 100 microtesla. In comparison, the Earth's modern magnetic field is only 50 microtesla. This wraps up the informational part of the video. Here are the references that I used in my video. Just like in my previous video, I'll link them down below. Okay, here is the space meme for today's video. Thank you for watching. If you enjoyed this video, please leave a like and comment. If I got anything wrong in this video, or if you have any critiques, feel free to call me out down below in the comments. Have a great day, y'all.